The digital universe is expected to hit 44 trillion gigabytes by 2020, which exceeds our storage capabilities. In order to make up for this lack of space, researchers have developed a technique that stores digital information within DNA. While the idea has been tried before, now researchers have encoded digital data from image files into a nucleotide sequence of synthetic DNA snippets and reversed the process to retrieve them, with zero data loss. The University of Washington, UW, and Microsoft researchers collaborated in working on shrinking the massive amount of digital data that could fill a Walmart supercenter to the size of a sugar cube. Life has produced this fantastic molecule called DNA that efficiently stores all kinds of information about your genes and how a living system works. It's very, very compact and very durable, said co-author Louise Sees, UW Associate Professor of Computer Science and Engineering. The researchers began by converting the long strings of ones and zeros in digital data into the four basic blocks of DNA sequences: adenine, guanine, cytosine and thymine. How you go from ones and zeros to As, GS, CS and TS really matters, because if you use a smart approach, you can make it very dense and you don't get a lot of errors, said co-author Georg Selig, a UW Associate Professor of Electrical Engineering and of Computer Science and Engineering. If you do it wrong, you get a lot of mistakes. The digital data was then chopped into pieces and stored by synthesizing a massive number of tiny DNA molecules, which can be dehydrated and preserved for a long time. In order to retrieve the stored data, the team encoded the equivalent of zip codes and street addresses into the DNA sequences, which allows them to easily find what they need. And using DNA sequencing techniques, researchers can read the data and transform it back into its original form using the street addresses to reorder the data. They have successfully encoded and retrieved digital data from images and videos. We demonstrate the feasibility of our system design with a series of wet lab experiments, in which we successfully stored data in DNA and performed random access to read back only selected values, reads the paper. We further evaluate our design using simulations to understand the error correction characteristics of different encoding schemes, assess their overheads, and make projections about future feasibility based on technology trends. DNA molecules are capable of storing information many millions of times more densely than existing technologies for digital storage, the researchers explained. All of the digital storage devices we use, flash drives, hard drives, magnetic and optical media, degrade after a few years. But using this new method will preserve information for centuries. However, the group does face one challenge, and that is making this method more cost-effective and efficient so it can be performed on a large scale. This multidisciplinary approach is what makes this project exciting, said Karen Strauss, a researcher at Microsoft and UW Affiliate Associate Professor of Computer Science and Engineering. We are drawing from a diverse set of disciplines to push the boundaries of what can be done with DNA. And, as a result, creating a storage system with unprecedented density and durability.